Good evening, everybody. We are starting chapter 16, which happens to be our very last chapter here that we're going to be studying here in chemistry. And I hope that you're quietly celebrating that because, of course, we don't want to let Miss Benson know that you are happy that this class is ending because she's going to miss you over the summer. So we are talking about acids and bases, and they're very important in our life. Our body is very in tune with acidic properties. Our body runs carefully on a very narrow pH. Our blood is a very good buffer, which we'll talk about that later in this chapter. We'll talk about our stomach acidity, our urine, and then we talk about the foods and the things that we clean with and the supplies that we use in our daily world. There's lots and lots of acids and bases out there. So the first thing that we're going to talk about is some very, very simple properties with acids and bases. And so if you would make sure that you're writing these down in your notes, let me grab a pen here. And we're just going to put some general properties down. We'll keep expanding on this list as we go through this chapter. But the first thing that you need to know that anything that you can recall or that you think about that tastes sour is going to have an acidic property. So like lemons or orange juice, citrus pop is acidic, and believe it or not, milk is very slightly acidic also. So things that are sour are going to be acid in nature. Things that taste bitter are going to be bases. Now, we may not know what bitter really tastes like, but those of you that had a little problems with your language, maybe since you've been growing up and got a little bit of soap in the mouth, not that would be any of you guys, that is bitter. Or real dark chocolate is a bitter taste. Or coffee can be bitter sometimes, so that would be bitter. Most of the bases that we have around us are cleaning supplies like toothpaste and shampoo and Windex, those type of things. We're going to talk a lot about the pH scale, which I know that you had in other classes before you have gotten to me. We know that acids have a pH that is less than 7. Bases have a pH that is going to be greater than 7. 7, sorry, that's the 7 there. And we also know that if I have a pH that's going to be equal to 7, that is going to be a neutral substance. And we are actually going to be doing later a titration lab that we are going to neutralize an acid and a base and try to see when it gets to the exact pH of 7. Now, in general, we're going to be talking about acids that they are going to produce hydrogen ions. And we know that when I say the word ion now, that is a charged substance. So they produce hydrogen ions. They're going to dissociate, and we will talk all about what that means. Bases can also be identified by how slippery they are. Hopefully you're thinking of soap, and soap is very slippery. It is a basic substance. And when we're doing one of our labs, we are going to do some feeling of an acid and a base, and you'll see exactly what I mean by that. As I just said at the beginning, that most food is going to be acidic in nature that we do eat, and bases are going to be things that are our cleaning supplies. So this is just some simple properties right now. We will add to this list, so make sure you save some room here. We're going to talk about indicators and some different theories that we're going to put into this column as we continue. So we're just going to cover one small section in this chapter, and the first thing that we're going to talk about is the Arrhenius model. Now, your book uses the word model. Often I have been taught that we use it as called the Arrhenius theory, and hopefully you're thinking to yourself, well, why is it a theory? We're going to be talking about 3 different theories with acids and bases: the Bronsted-Lowry theory and Lewis acid and Lewis bases theory. And all this is about is trying to identify all substances as either an acid or a base, or when we get to Bronsted-Lowry as a neutral substance. Now, the Arrhenius theory says that everything produces a hydrogen ion in an aqueous solution. Well, this stands up. This isn't anything that we've been able to disprove. However, for a base, it says that we produce hydroxide ions in an aqueous solution. So we're going to hold on to that thought for just one second. So if we take a look at this example right here, we all know how to write hydrochloric acid. We know that hydrochloric acid is HCl. We know that it is aqueous, meaning that we are making it with water, and that when we put it in water, it is going to fully dissociate. And the reason it's going to fully dissociate is because it is a strong acid. And we'll talk about strong and weak acids in the next couple of sections. For right now, we're just going to leave it as a strong acid that it fully dissociates. And so what that means is it fully ionizes and it breaks apart into our hydrogen ions plus our chloride ions. And you can see with both of these, again, we are saying that it's an aqueous solution. So remember when we talk about this all the time that I have been trying to tell you that you need to make sure you keep your pictures straight and orderly so you understand what's going on. So if this is my acid right here and I'm pouring in my HCl, because it's fully dissociated and because it's very strong, we are going to have hydrogen ions swimming around in here. Remember that there's going to be some collisions that are going on in here. In addition to that, we are going to have these chlorine ions, and they are going to be swimming around here as well with this negative charge. And so we have all these different ions moving around in here in this aqueous solution. And the same thing will happen if I take a look at my bases. And here I have sodium hydroxide. And again, this is going to be a strong base. And so because it is strong, it is also going to fully dissociate. So you should be able to quickly write this out that NaOH, in a aqueous solution dissociates into a sodium ion, aqueous, plus a hydroxide ion. And it is all balanced, be 1 to 1. So I have written the correct equation. Again, if I was drawing my picture like I did over here, I would have my sodium ions and my hydroxide ions. Now, hopefully you're thinking to yourself, do all bases produce a hydroxide ion? And you don't have to go very far in your home to say no to that answer. Hopefully you have some toothpaste or some baking soda or something like that, and they do not produce a hydroxide ion. So what had happened is we started with the Arrhenius model, the Arrhenius theory. He was the first one that tried to classify acids and bases. Then came along the Bronsted-Lowry model, or the Bronsted-Lowry theory. And so this was a more general theory. And so what he is saying that is an acid is a proton donor. We are still going to say that it is a hydrogen ion, but if you think about hydrogen, we know that hydrogen has its one lone electron around on the outside. Well, in order to have that +1 charge, we know that that has been transferred, it has gone away. Well, what is left in beside is a 1 proton. So all I have left is a proton here, which has a positive charge. That's where they get that it's a proton donor. Then a base is going to be a proton acceptor. Much more general, it would include everything like baking soda and our toothpaste that the Arrhenius model is not able to identify. So the general reaction for an acid dissolving in water is this: HA, meaning H for the acid, A for the anion, aqueous solution again, water yields, this is called the hydronium ion. Now I'm going to show you a shortcut in just a second, but a lot of times when we are trying to figure out what essentially each part of this is, we need to know that H3O is a hydronium ion. And then we have the anion, which is the separation of this acid over here. So we'll continue to talk about this, but a shortcut, I just want to write that here really quick, we'll be coming back to this later. You can see that if I write my acid, my general formula for an acid, this is going to dissociate into my hydrogen ion plus my anion. Well, we also talk about this in terms of our conjugate acid and conjugate base pair. So if you see, I wrote my HCl in water this time, I didn't take the shortcut, and I have my hydronium ion and I have my chloride ion. Well, if I take a look at the pairs, you can see HCl is paired up all the way over here with my chlorine, and then I have my water paired up here with my hydronium ion. So what we need to see is that when I am doing this, can you see that this hydrogen is being donated? All right, so I do not have that anymore. And so this is donating a hydrogen ion. Well, when I take a look at what that means is I have a proton donor. It is donating that hydrogen ion. So as you would suspect, that this HCl is going to be my acid, and the pair with it is called its conjugate base. Conjugate base meaning conjugate, it's connecting to it. So this will have some basic properties. And then on the other side of it, I can see that this water has accepted something. It has accepted a hydrogen ion. So this is accepting. So this makes this the base, and this makes this the conjugate. Let's see, I'll write it down here. This is going to make this the conjugate acid. So it has acidic properties. So let's take a look at some other examples so you can kind of see this again. So we have an example of ammonia dissolved in water. Plain old ammonia is just going to be your Windex. So if I do my conjugate acid with my acid and conjugate base, excuse me, and my base with my conjugate acid. So how do I identify that? Bracket them up. You can see I have nitrogen here, I have nitrogen here, I have hydrogen and oxygen here, and I have hydrogen and oxygen here. So if I take a look at this NH3 is accepting a hydrogen ion. It went from 3 to 4. So when it is accepting, this makes this the base, and this is going to be its conjugate acid. Down here then, I can see my water has donated a hydrogen ion. So because it's donating, it is going to be the acid, and this is going to be the conjugate base. All right, moving to the next example. We kind of already talked about this one a little bit. So again, bracket them up. I have hydrogen and chlorine. Here's my chlorine. I have water, hydrogen and oxygen. Again, the same formula. So if I take a look, this is donating a hydrogen. It's not there anymore. It went somewhere else. So because this is donating, this is going to be my acid, and this is going to be my conjugate base. Then this is going to have to be my base because it is accepting a hydrogen ion. So this will be my conjugate acid. Now, I hope that you're looking at this and scratching your head a little bit, because you should be, sorry, I'm trying to select a different color here so you can see this, that if I take a look here, I have water in one situation acting as an acid, and then I have water in the other situation acting as a base. So this is another flaw in this theory. Water is actually amphoteric. I'll let you think about that for a second, that word amphoteric, and we will study that in the next section. So that's it for this section, and we're going to take a look at homework 1, some more examples to be able to identify bases and conjugate acids and the partners and the pairs in these equations. Have a wonderful day, and I will see you soon.